So, well, you might know me already, or if not, well, I'm presenting myself. I'm Antxon Arrizabalaga, a visiting student from Mondragon Universitatea in the Basque Country, in the north of Spain. And I'm going to be, well, I've been here in Knoxville with Dr. Tolbert for the last 5 months, and he asked me to do a presentation about my PhD, and this is what I'm doing today. So thanks everyone for coming, and I hope you can learn something today. I also know that there is people from my home university in the Basque Country watching, so thank you guys for watching and tuning on. I can't wait to go back home. It's going to be just in a week. So, well, this is the title of my PhD, even though we might revisit it later. Yeah, seeing what we have done during these years. And this is the content that I'm going to present today. First, I'm going to briefly introduce my home university, Mondragon Universitatea, and then present the background of this research project. I'm going to make a little introduction to wind energy and silicon carbide devices, and then talk about the LCoE analysis that we did and the laboratory prototype that we built in our home university. I'm gonna finish with the future work I want to do and how I would like to finish my PhD. So Mondragon Universitatea, well, as I said, we are located in the Basque Country in the north of Spain. You can see here in the map, and we have different campuses all around the territory. The headquarters are in Mondragon, but my office and my laboratory are in Hernani, and I live in San Sebastian. So it's very close. It will be like Oak Ridge and Knoxville, for example. It takes me 10 minutes to get to work every day. We have researchers, projects, and students all around the world, but I think that we have to add one more point here, right? Because I've been trying my best to survive to the winter in Knoxville, so I think I deserve a bit of credit here in this map. Regarding the founding of this research was founded by a big wind turbine manufacturer that offered funding for 2 years with the objective of analyzing the impact of silicon carbide in wind energy systems. And they expected experimental results. So what we proposed was to find one or more business cases in where silicon carbide devices could affect positively wind energy systems and do that analysis theoretically. In the second year, we would like to increase the accuracy of our analysis with experimental tests. However, the objective of the PhD is a bit wider. We mainly want to obtain knowledge in high-power silicon carbide devices, and we saw that we had the opportunity to create a high-power laboratory in Hernani, in our San Sebastian campus. The Electric Energy Research Group is the research group that I belong to, and these are the topics that we work in this research group. So as you can see, this project is totally aligned with the topics that we work in our research group, because we have medium voltage with silicon carbide devices, we have grid integration with renewable energies, we have power electronics nearly everywhere, and we had the opportunity to build our high power laboratory in Hernani. This picture was taken 1 year ago when I first started building the laboratory. So as you can see, this laboratory is very recent. Okay, any questions so far until this point? Yeah, can you go a little slower? I'll try. Thank you. Okay, so let's jump to the introduction, and I'm going to present the 2 main configurations that nowadays are used in wind energy. The first one is called the DFIG configuration, and is based on a doubly fed induction generator. As you can see here, the power converter is only connected to the rotor, and the stator of the generator is directly connected to the grid. So the power converter has only has to manage only the power in the rotor, so it's smaller and cheaper. However, the generator needs to work at high speed. So we need mechanical gears here in the shaft of the generator. And we also need brushes to connect the rotor to the electrical grid. So the maintenance of this configuration is more costly. The second configuration is called the full converter configuration and is usually based on permanent magnet generators. As you see in the figure, the power converter manages the whole power of the system. So the generator is fully decoupled from the grid. Of course, the power converter is bigger and is more costly, more expensive, but the generator can work at low speed. So we don't need any mechanical system in the shaft of the generator. This makes the maintenance of this configuration cheaper and easier, and is preferred for offshore wind energies, offshore wind energy, for example.
Yeah, who designed the generator?
Who designs the generator?
Yeah.
Well, the company. I mean, not us, not us.
Yeah, in Dr. Wang class, I asked why there on a few universities have professors research for the motor or generator design. Very few, but the market is very promising.
We have a research group that is called Electrical Machines, that they are in charge of designing the generators for this company. And I don't think they design generators for wind energy in particular, but yeah, the knowledge is there. Yeah.
Probably mature technology.
Sorry?
Probably mature technology. There's only so much you can do.
Yeah. Okay, so when analyzing energy sources, the most important metric is the levelized cost of energy, or the LCoE. This will tell you how competitive an energy source is in the market. It's a ratio between the cost of your system and the energy that you're able to generate. As you can see here, nowadays, wind energy and solar photovoltaic already outperform traditional energy sources like the coal, for example. And it's important to highlight that due to the evolution that energy sources, renewable energy sources are having, the trend is to improve the LCoE, whether in traditional energy sources, as these technologies are already very mature, the LCoE is kept constant. Our project also involves silicon carbide, so I want to make a little comparison of the characteristic of silicon carbide normalized to the silicon. I want to highlight three main characteristics. The first one is the breakdown electric field that relates to the ratio of the on resistance of your device and the blocking voltage capability. The second one is the electron saturation velocity. We see it here, and relates to the switching speed of your device. So we can switch faster and more efficiently with silicon carbide devices. And the third one is the bandgap energy of the technology. And this relates to high temperature operation and the high blocking voltage capability. So silicon carbide devices are preferred to work in high voltages. These characteristics allow us to use silicon carbide MOSFETs in applications in where up to date or today, silicon IGBTs needed to be used before, okay? This is important because, as I said, silicon MOSFETs are better in switching. They have no tail current in the turn-off, they can switch faster, and the switching losses can be reduced. Okay, any question up to this point? So I'm going to jump and start presenting the LCoE analysis that we performed in our PhD. Of course, to analyze something, we need an equation, and this is the one that we used. Remember, the LCoE is the cost of your system divided by the energy production. So here we have the CAPEX that relates to the initial investment in your system. We have the cost of the wind turbine here, the cost of the civil engineering, and a factor that relates to the taxes. Then, of course, we have to consider the OPEX that relates to the operational costs of your system. And we have to take or consider the company margin. That is the benefit that the company will get from that system. The system cost is divided by the weighted annual energy production. That is the energy that you can produce during 1 year, but averaged depending on the wind profile of your location. And you have to subtract the losses. These losses are related to the hours that your system is not able to work because you are performing maintenance works, for example, or you had an unexpected failure. So with this equation, we developed an algorithm. I know this algorithm looks like a big monster, but please focus in the heart of the algorithm, that is the LCoE calculation function here. Remember, it's a division between the system total cost and the energy that you can produce. We program this in MATLAB, and we start the whole algorithm with a mechanical model. You introduce the wind profile, the application power, and the configuration of your system to the mechanical model, and you obtain the power of your converter. Then, considering the semiconductors and the switching frequency, you apply the converter loss model to that power of the converter, and you obtain power losses here. So with the power losses, we can easily compute the annual energy production and some other things such as the cooling system, for example. So we already have our energy production, and we need to calculate the system cost with the cost function here. We consider several things such as the OPEX, the company margin, the filters, the different semiconductors, different data. And we obtain the LCoE of one configuration. But remember, the objective is to compare several configurations. So we need to add one external loop to this whole algorithm in where we change one input variable and we start again. Of course, the results will be stored in Excel, in a database in Excel, to post-process it and analyze the results later. So you may ask, which are the input variables that we change in this algorithm? Well, I show them here. We change the power of the application. We change the configuration. We have the defig and the full converter configurations here. We change the switching frequency, the voltage rating of the configuration, the topology of the power converter. We consider 2-level and 3-level converters, and of course, the semiconductors with different technologies, silicon and silicon carbide, and different voltage levels of the semiconductors. To do so, we had to build a database of semiconductors, model each semiconductor, and assign a cost to each semiconductor. This was pretty hard to do, and we had to do some assumptions that will introduce a little error in our calculation tool. But you always need to consider assumptions when you calculate the LCoE, because there is a lot of data coming into this algorithm. So we ran our tool.
So this program is just to estimate the cost, right? It's not an optimization program.
It's an LCoE calculation tool. So this algorithm will calculate not the cost, not only the cost. It will calculate the LCoE of the whole configuration. Yes, it's not an optimization tool. It's a calculation tool. The optimization will come later. We will analyze the results of the LCoE, we will compare them, and we will decide which configuration is the best.
Yeah. So how accurate so far compared with your actual cost and your estimated cost?
Sorry?
I mean, the accuracy of this program.
Okay, I'll show you now. So related to your question, the first thing that we did was to tune the tool in order to get the LCoE of the baseline. The baseline is the product that the company offers nowadays. So they know the LCoE of their product. So we introduce the data of their actual product of the baseline, and we make sure that we obtain the same LCoE as they obtain, right? And from there, we start running. We saw that we had over 67,000 cases to analyze. And remember that the objective of this tool is to have a live tool. So if the company gets a new cost for the filters, for example, they can easily access the cost of the filter in the tool, change it, and run again. Or if a new semiconductor comes to the market, they can model the semiconductor, introduce it to the database, and run again the whole program. So the computational cost of this program was too high to perform that objective. So we decided to take advantage of the characteristics of MATLAB, that literally stands for Matrix Laboratory, and it's very good performing vector and matrix operations. So we changed input variables into vectors. So now, for example, the switching frequency is not a number, it's a vector of 3 numbers. And every time that we use the switching frequency in a function, we will run that function once, but calculate the function for the whole vector and perform vector operations. We reduced the computational cost 70% doing this. Of course, some variables cannot be turned into vectors, such as, for example, the semiconductors, because as I said, it has a database that needs to be accessed every time. And when you perform vector operations, when you multiply vectors with vectors, you obtain matrices. So the results were compressed in big matrices that we had to decompress in order to store them in Excel. We did this in MATLAB using indexing. It's pretty easily done, but of course we had to rethink the programming structure of the whole program. Here I want to give credit to Aitor Idarreta, who's a student of Mondragon University, who did an amazing job with the program and helped me a lot during this process. So we ran it and we obtained 67,000 points in a map, and we can see nothing here, right? Well, that's not true. We can see something. So if you see the left low corner here, we already see that there are some configurations that improve the LCoE. Remember, we saw that all the configurations that improved the LCoE of the baseline were diffig configurations. So now we focused on the topology that was used in those configurations, the power converter topology. And we saw that all the configurations used a 3-level topology. This was the first big result of the PhD. 3-level topologies can improve the LCoE of the baseline. However, when we analyzed the technology of the semiconductors, we saw that all of the semiconductors were silicon-based. All of the configurations were silicon-based. So none of the silicon carbide configurations could improve the LCoE of the baseline. We got a big win, a big W with the topologies, and we got a big L with the semiconductors. Of course, the project is all about analyzing the impact of silicon carbide. So we decided to specifically analyze the configurations with silicon carbide. And we saw that the cost of the silicon carbide was holding back those configurations. So we decided to reduce the cost 50%, 1/2, and see and analyze the configurations with silicon carbide now. And we see that with the reduced cost, there are configurations that can improve the LCoE of the baseline. And unlike with silicon, we see that there are 2-level and 3-level topologies, both improving the LCoE of the baseline and competing between each other. Of course, if you are building a 2-level topology, you need 1700 volt semiconductors, whether if you are building a 3-level topology, 1200 volt semiconductors are enough. So we decided to further study the impact of the cost in the silicon carbide semiconductors, and we also added the effect of the switching frequency, because remember that silicon carbide semiconductors are good at switching. So please focus on the brown line here, that is the 2-level topology with silicon carbide and original switching frequency. And now compare it to the two-level silicon carbide with increased switching frequency. We see that increasing the switching frequency with silicon carbide can improve the LCoE of the original switching frequency. This is because, as I said, the silicon carbide is good at switching, so it keeps high efficiency even at high switching frequencies. High efficiency means high energy output. And with increased switching frequency, you can reduce system, such as the filters, for example, right? So the LCoE will be improved with increased switching frequency. Another big conclusion here is that we already have our three base business cases, because we see that the three-level with silicon and original switching frequency, the three-level with silicon carbide and increased switching frequency, and the two-level with silicon and increased switching frequency are going to improve the LCoE of the baseline and are going to compete between them in the near future. We think that, this analysis is based in the fact that, or in the theory that the price or the cost of the silicon carbide semiconductors will be reduced in the following years. So now that we had our business cases, we needed to analyze the commercial indicators. These are indicators that do not affect the LCoE, but are important for industry because they are affected by the company strategies, the market, the company agreements between them. So we decided to analyze the time to market, the technical risk, the development effort, and the supply chain availability of the business cases and compare them to the baseline. Of course, the baseline is not affected by these commercial indicators, but in the case of the three-level with silicon, the commercial indicators are worse. Why is that? Because you are introducing a new topology in your product, so you have to perform tests and develop prototypes. Of course, the supply chain is not affected because you are still using the widely used silicon semiconductors. This is worse with silicon carbide because you are using a new technology, so the technical risk is higher, the development effort is higher, you have to test the technology, you have to test the semiconductors, you have to build new prototypes, and the supply chain availability is not as good as the silicon semiconductors, because remember that silicon carbide high power modules are not as popular as the silicon IGBTs nowadays. The trouble is double with the three-level silicon carbide, because not only you are introducing a new technology, but you are also introducing a new topology. Okay, so as a conclusion of this chapter, we saw that the DFIG can improve the DFIG has better LCoE, the three-level with silicon can improve the LCoE of the baseline. The silicon carbide can be competitive if the cost is reduced, and increasing switching frequency is positive for silicon carbide. We had our three business cases: the two-level with silicon carbide, the three-level with silicon, and the three-level with silicon carbide. Any questions so far with this analysis? Yes, Eleanor.
Back on slide 19, did you go there? Did you consider hybrid ones in this? I know in the previous you considered hybrids. Did you consider hybrids with a 50% reduced cost?
No, because this analysis was focused in the full silicon carbide semiconductors. Here we considered hybrid ones, but we saw that in the commercial indicators, all the hybrid configurations were discarded by industry because they think that the manufacturing of the hybrid modules will be not very popular in the future and mostly very personalized, or like they will build certain amount of modules for certain companies only. It won't be something massive. Okay.
And John, tell them what you mean by hybrid.
Okay. Oh yeah. This is when I write a hybrid SiC here is a silicon IGBT with a silicon carbide diode in parallel. So the diode will improve the switching characteristics of the module, but the conduction will be performed by the silicon IGBT. These are highly used now, well, highly used. They are starting to use them now in certain applications, but they are very specific applications. For example, railway applications. So that's why we didn't consider them, because the company thought that, yeah, the manufacturing of these hybrid modules will not be massive or industrial. Okay, so I'm going to present the laboratory prototype that we did in our new laboratory in Hernani. We wanted to have a flexible prototype in where we could test 2-level, 3-level, silicon carbide, different topologies, different technologies, but we wanted to be simple with a common power stage and the same control board. The objective was to increase the accuracy of our LCoE calculation tool and verify the results that we obtained from that theoretical analysis. And of course, from the PhD point of view, we wanted to develop the high power laboratory in Hernani, and we wanted to obtain knowledge in the application of silicon carbide modules. For that, we wanted to test the efficiency, the effect of the switching frequency in silicon carbide modules, and overall system level impact when you introduce silicon carbide semiconductors. So the approach was to buy a commercial bus regulator here, connect it to the 3-phase grid, and build a DC link. And then to that DC link, connect our prototype, the 2-level converter or the 3-level converter. The modules in these prototypes are replaceable, so we can switch easily from silicon to silicon carbide. Here, I want to highlight a design, and a specific design that we did for silicon carbide. It's the design of the bus bar of the 3-level converter. We did this with the objective of minimizing the inductance of the power loop, so we could switch fast and efficiently, but having the overvoltage under control. To do so, we optimized each phase individually, and we made sure that we had symmetrical current paths by using a specific module placement. As you see here, we shifted the module 3 and we rotated. We used optimized capacitor placement by connecting 2 capacitors in parallel and in opposite directions. So we were forcing opposite currents here, and we could take advantage of the magnetic cancellation concepts. And finally, we actively overlapped the neutral layer to the whole switching loop. As you see here, the neutral layer doesn't cover the whole switching loop. And there is a non-overlapped area here, whether in the optimized neutral layer, the neutral layer overlaps the whole switching loop. So it allows opposite currents in the whole switching loop, taking advantage of the magnetic cancellation concepts. We tested our design, measuring the impedance with an impedance analyzer, and we saw that with the specific module placement, we reduced the asymmetries in the current path 90%. With the optimized parallel capacitor placement, we reduced the inductance of the capacitors nearly 80%. And with the overlap neutral layer, we reduced the inductance of the switching loop over 80%. The last step was to test this design and actually switch the bus bar. This is the waveform we obtained from the double pulse testing. We were able to switch up to 800 volts, which is a very ambitious voltage for 1200 volt devices, but we could do this because the overvoltage was under control. And we saw that we were still switching very fast in around 30 nanoseconds, which is a very high speed switching speed for high power modules. So the design was a real success. If you have interest in this design, we are preparing a publication right now, and I will be happy to share information with you. So just contact me, and yeah, I will let you know. Here I show the two-level converter that we built. You can see the DC link capacitors, the gate drivers, the air fan here, the controls over here, and the power modules are underneath the bus bar. And here we have the output waveforms of this two-level converter. This is the three-level converter. Remember, each phase was designed individually. So phase A, phase B, and phase C with the drivers, the capacitors, the air fan. The modules are again underneath. And in this converter, the control board is on the other side. And these are the output waveforms. Of course, as it is a three-level converter, the line-to-line voltage has to have 5 voltage steps. So we had 1, 2, 3, 4, and 5 voltage steps in the line-to-line voltage. So we also analyzed the effect of the switching frequency in the two-level converter. We compared the efficiency of the two-level converter with silicon and the efficiency of the two-level converter with silicon carbide with increased switching frequency. And we see that the silicon carbide keeps a very high efficiency even at high switching frequency, around 98%. Whereas with silicon, the efficiency drops drastically when you increase the switching frequency. So we verified the results obtained by the LCoE calculation tool. We can still have a high energy output with silicon carbide, even at high switching frequencies, and reduce the filters, for example. We also tested the business cases comparing the efficiency of the two-level silicon carbide with increased switching frequency and the three-level silicon with original switching frequency. And we saw that we still have a little more efficiency with the two-level silicon carbide at increased switching frequency, but they are competing between them. And they both outperform the two-level with silicon. Again, we verify the results obtained by the LCoE calculation tool. So as conclusions of this chapter, well, we validated the results obtained by the LCoE calculation tool with this analysis, and we finished the project with the wind turbine manufacturing company. And regarding the PhD, well, we built the laboratory and it's running. We could perform good tests and measure the efficiency and the effects of the switching frequency and so on. And here I want to give credit to Tiria, who is an undergrad student of Mondragon University, who helped me build the high power laboratory in Hernani. I want to finish this chapter highlighting some upgrades that we are performing to the high power laboratory in Hernani. We have installed a security cage. I'm hoping that we are buying some new measurement equipment and new passive loads so we can increase the power of the tests. And I want to mention that we are open for new research opportunities with UTK. So if you think that there are some good ideas or good tests to resolve, some analysis that you think that you can do with our prototype, I'm going back home in a week, so I'll be happy to perform the tests. Yeah, do some collaboration projects. Just let me know. Any questions so far in this chapter? Yes.
On slide 30, I'm just trying to see how your power modules were attached. Are they attached to heat sinks?
Yes, yes. So imagine a sandwich. We have the heatsink, the modules, and the bus bar. That's the order.
So the heat sinks are sitting on top of the DC plates?
No, the heatsink is underneath, and the modules are, so it's the heatsink, the modules are connected to the heatsink, of course, to evacuate all the heat, and then the bus bar is connected. The metallic plate you see here is the bus bar that is connected on top of the modules, and it has the capacitors connected to to that layer, to that aluminum layer.
And the AC and DC bus bars are on top.
Mhm.
Right, Antxon?
Yeah. This is the AC bar here, is on top of the module at the same, maybe a photo, a horizontal photo would be helpful here, but the AC bar is here on top of the module, and the capacitors are also on top of the other modules. The structure is here. So there are two modules that we cannot see because are underneath the bus bar in vertical position, and this is the AC module that is rotated and shifted. That's the one that we can see here. This one.
Okay, so how far are the gate drivers from the modules? Are they sitting right on top?
Yeah, they are right on top.
Okay,
Yeah.
maybe it's just circuits. Is
Yeah.
there a reason why you put the capacitors on the top instead of on the bottom so they could get blown on by the fan?
Yeah, we didn't consider refrigerating the capacitors. We didn't think that it was necessary. There are some designs in where you switch the direction of the capacitors and the air goes through the capacitors too. Yeah. Not in our case. Okay. Any more questions?
Do you see differences when you, or have you looked at placing the modules, the switching devices as close as possible? Do you see a significant difference if they're like the one that's, instead
Yeah.
of having them 1, 2, 3, you have the one rotated?
Mhm.
Is it more of a benefit to have your tie-ins together closer than if they were just next to each other?
The thing is that if,
Or is that just mechanically how you guys
yeah,
do it?
yeah, it's related to the pinout of the modules. So you mean having this module up here, right?
Yes, is it more advantageous to do it that way than if they were?
Yes, because if you have this module up here, due to the pinout of the modules, your current paths cannot be symmetrical. So you will have imbalances in your parasitics in the power loop. So in order to have symmetrical current paths, you need to rotate the module and place it here. If not, you cannot achieve symmetry due to the pinout of the modules. You will have to connect this terminal to this terminal, this terminal.
So I think that's why in most cases that I've seen they're like this. Instead of this way, they're 90 degrees.
In 3-level converters or 2-level converters, because that's a main difference. In 2-level converters, you can have them in a line. There is no problem in 2-level converters, but in 3-level converters, as you have this AC module here, that's the problematic module. And also, it depends on the package of the module that you are using. In our case, the package of the module is, so it's high side, low side, and middle point or AC connection. There are some cases that connection is not like that. It's high side, middle, and low side. And then the layout has to be different. So the layout and the orientation and the layout of the converter totally relates to the pinout of your modules.
That's the difference.
Mhm.
Antxon, I think Jing Jing might have a question.
Okay.
Ask her.
Jinjing, do you have a question?
Thank you. So on page 32 about the frequency,
Yes.
yeah. So here I see the maximum frequency is 10 kilohertz. Is it possible that we further increase the frequency? And if we further increase it, will the silicon carbide based prototype keep still kind of flat efficiency curve of the efficiency?
Yes. We only analyzed until 10 kilohertz, but yeah, as you say, Jinjing, we could increase further in silicon it gets very hard to work higher than 10 kilohertz with silicon carbide because, as you see, we have unacceptable losses already with. Sorry?
Misspoke. It's harder with silicon.
Oh, yeah. It's harder with silicon. Yeah, that's what I meant. I don't know what I said. Sorry. So yes,
Okay,
we could increase the switching frequency more with silicon carbide. Yes, I think so.
Okay, yeah. Yeah, I'm just curious if we further increase the switching frequency, will the efficiency of the silicon carbide based prototype still have a very flat curve and keeping a higher level? That will be much better.
Yeah, that would be very interesting. In fact, yes, Jinjing. However, you have to consider that the application of this prototype is wind energy. So we are trying to maximize the energy output of our converter. So losing 1% efficiency can be critical. So we have to really try to maximize the efficiency of our prototype. For example, in other applications, such as railway, for example, you can increase more, or I don't know, maybe other applications that are not this one.
Okay.
Thank you, Jinjing. Okay. So the final section, the future work and the end of the PhD. It's interesting how everyone is talking about how fantastic silicon carbide is, how efficient it is, how fast it switches, but nobody is talking about the challenges of the silicon carbide, because when we switched from silicon to silicon carbide in our laboratory, nothing worked. Absolutely nothing worked. So I think it's a big contribution to make a list of the challenges that we faced, try to explain them so the designers will understand the phenomena that is going on in their system and how we solve them, on how to solve these new challenges. The first challenge that we faced was the false turn on that I show in the left-hand side here. This is the very first switching that we did with silicon carbide. It's a very low current switching, but as you see, there is a short circuit here with a huge current spike. This is because the switching of the lower switch turns on the upper switch. This phenomena will hardly ever happen with silicon IGBTs because the switching is so slow that the switching of one device is not affecting the switching of the other device. We solved them. We solved the issue. And here we are switching 5 times more current, and the current spike is way lower. So we solved the problem. Okay, by analyzing the gate driving circuit and changing the gate resistors of your driver. Yeah, there's a relation there because you can slow your gate, but having a higher resistor makes the voltage drop in your gate circuit bigger too. So there's a trade-off there. The second thing that we saw was the reverse recovery, that you have to consider. Silicon carbide high power modules have a pretty bad body diode, as you see here, with a high reverse recovery. So you have to make sure that you consider this energy when you're analyzing the switching energy of your converter. And finally, you have to make sure that the measurements and the protections that you are using in your converter are suitable for silicon carbide. When we first started in our laboratory, I remember that I took the voltage probes that we had in the laboratory. Imagine we had 10 probes, 8 of them didn't work for silicon carbide. They had, their bandwidth was too low, so we couldn't measure our fast switching. The switching of the silicon carbide is very fast, so you have to measure even faster, of course. And as the silicon carbide has high DVDTs and DIDTs, it is very susceptible to parasitics. So you have to really be careful when you set up your measurements. You might be affecting the circuit and introducing parasitics with your measurement equipment. We suffer this too. In addition, you have to have suitable protections. So, for example, we were detecting this at operation when we didn't have any short circuit because those DVDTs were affecting the sensing circuit. You also have to consider that if there's actually a short circuit in your module and you turn it off too fast, you might provoke over voltage in the device and destroy the device, not from the short circuit, but from the over voltage. So there are devices that there are drivers that have this two-step turn off already programmed in there, and they turn off the SiC devices slowly in order to control that overshoot. So these are things that designers need to consider when switching from silicon to silicon carbide. This phenomena, all these challenges are not new for high frequency designers, but for high power guys like me in this case, these things are new. With silicon IGBTs, this phenomena will never happen. So I think it's a big contribution to show what's going on and really how to solve them. So finally, end of the PhD, yeah, I want to present my finish my dissertation by October 2022, defend it in December 2022. We hope to have Dr. Tolbert there in the Basque Country with us for my defense and hopefully graduate successfully and become a doctor. So thank you, eskerrik asko, as we say in Basque. It's been a pleasure, guys.